Hello and welcome to another WJEC A level physics question. This is from the June 2014 Unit 2 exam and it's question number 3. It's a question basically about diffraction gratings. First of all, the question asks us to describe a diffraction grating. So here all we're going to say is that it's a piece of transparent material, something like glass, with many lines on it. And those lines are very close together. They're parallel. And they're evenly spaced, and they're also very, very fine. Very narrow. We're talking literally hundreds of thousands of lines per meter on a diffraction grating. Second part of the question tells us that a particular grating has 400,000 slits per meter of its width, and we've got to show that the distance between the centres of the neighbouring slits is 2.5 micrometers. So this is just a simple case of taking 1 meter and dividing it by the 400,000 lines that there are on that meter of the grating's width. That's what we get the marks for. If you type it into the calculator, you get 2.5 times 10 to the minus 6 meters, which is of course 2.5 micrometers. Next part of the question tells us that the laser beam is shone normally at the grating, and we get second order beams leaving the grating at angles of 25.2 degrees, and we have to calculate the wavelength of the laser. So as soon as we realise it's a diffraction grating question, we can use n lambda equals d sine theta, and hence lambda is d sine theta over n, d being the 2.5 times 10 to the minus 6 that we just worked out, theta being 25.2 degrees, and in this question it's the second order, so n is 2. If we put those numbers into the calculator, you'll end up with 532 nanometers. And remember, if you do have a Casio calculator, use that ENG button to put the answer into nanometers so that you can make the simple check that the wavelength is somewhere in the visible range of the spectrum from roughly 400 to 700 nanometers. The next part of the question asks us to find the angle for the third order beam. So if we rearrange the equation, theta is going to be sine minus 1 of n lambda over d. So sine minus 1 of 3 times that same wavelength, 532 nanometers. Remember to put the nano back in and use the answer button on the calculator to avoid rounding, over the 2.5 times 10 to the minus 6 for d that we calculated earlier. For this part of the question and the previous part, obviously make sure that your calculator is not in radians mode, that it's in degrees mode. Typing those numbers into the calculator gives us an angle of nearly 40 degrees, 39.7 degrees. Finally, the question asks us why the beams of the different orders are much further apart with the grating than in a Young's double slit type experiment, and that's simply because the slits are much closer. So the gap between them is much smaller in the diffraction grating. Or you could phrase this the other way around and say that the slits are much further apart with the double slit experiment. That's all you need for the marks, but a quick explanation. If we use our double slit formula, lambda equals a delta y over d, and rearrange for delta y, we get lambda d over a. And here you can see that there's inverse proportionality between the separation of our fringes, in other words how far apart our beams are going to be, and the distance between the slits. And once again, the slits in the diffraction grating are far, far closer together than they are for the double slit experiment. Thank you for listening. Please like and subscribe.